Statistical analysis cannot operate on the fluid nature of human behavior. To analyze subjective characteristics, we must first translate them into rigid numerical structures. This process is measurement, the standardized assignment of numbers or symbols to an attribute based on a strictly pre-specified set of rules. These numbers provide a universal language for research, allowing different teams to communicate results and test the same hypotheses with mathematical precision. However, if the rules governing those assignments are flawed, the resulting numbers cease to represent the characteristic they were meant to capture. The scientific rigor of a study is dictated by the specific architecture of the scale used to generate its data. Data is only as useful as the mathematical and causal rules that govern its creation. We can view measurement as a hierarchy of scale calibration. At the foundation is the nominal scale, which offers the most basic form of data organization. Nominal scales sort subjects into mutually exclusive and collectively exhaustive categories. In this system, assigning a 1 to males and a 2 to females creates a label, not a mathematical value. These numbers allow for frequency calculations, but possess no intrinsic meaning. The ordinal scale introduces meaningful rank ordering. It keeps the categorical sorting of the nominal level, but adds a sequence. While an ordinal scale shows the order of items, it cannot determine the distance between those ranks. In a survey of job characteristics, an employee might rank independence as their first choice and pay as their second. However, they may value independence significantly more than pay, while their second and third choices are nearly identical in importance. These base scales group and order responses, yet they leave the exact magnitude of the differences between those responses unknown. This gap is bridged by the interval scale. Here, the distance between any two neighboring values is mathematically equal. This consistency permits researchers to calculate the arithmetic mean and standard deviation. This creates a unique situation with Likert scales. While strongly disagree to strongly agree is formally an ordinal ranking, researchers often treat these responses as interval data. Adopting this assumption allows for advanced testing impossible with simple rankings. The highest here is the ratio scale. It possesses all previous properties, but introduces an absolute, meaningful 0 point. A true zero allows for proportional analysis. We can state with mathematical certainty that an income of $100,000 is exactly twice the magnitude of an income of $50,000. Because data structure dictates the limit of what can be calculated, researchers must use the highest calibration scale the variable allows. Establishing a powerful scale is only half the battle. We must then verify that the scale is functioning correctly in the field. This is the goodness matrix, which evaluates a measure based on two distinct pillars, reliability and validity. Reliability measures consistency, confirming the instrument produces stable results. Stability is tested over time, while internal consistency ensures all items hang together. Validity tests accuracy, confirming the instrument truly measures the intended theoretical concept. We establish this through content validity, which ensures we've captured the entire domain of the topic, and criterion-related validity, which tests if the measure predicts future outcomes. Finally, construct validity ensures the empirical results align with the theories used to design the test. An instrument can be perfectly reliable, returning the same score every time, while remaining completely invalid. Scientific rigor requires both. Identifying a scale's goodness requires understanding a hidden mechanical factor, the causal direction between the concept and the questions. In a reflective scale, the data originates from the underlying construct. The psychological state of the subject causes their responses to the questions. Because one concept drives every answer, all items in a reflective scale should correlate. If the core construct changes, all responses shift simultaneously. Formative scales function in the opposite direction. Here, the construct is an explanatory combination of independent indicators. In this model, the items generate the construct. We see this in the job description index, where satisfaction is a composite of different factors. An employee can be highly satisfied with their pay while simultaneously having no promotion opportunities. These dimensions are independent, they do not correlate, and they are not expected to. In a formative scale, a change in one indicator alters the total score even if the other indicators remain stagnant. This creates a critical point of failure in research. If a researcher applies an internal consistency test, like Cronbach's alpha, to a formative scale, the lack of correlation will make a perfectly accurate scale appear broken. Testing a formative scale for inter-item consistency is a category error. The resulting low score isn't evidence of a bad scale, it's a reflection of the scale's inward-facing causal design. Every survey and data point sits within this logical architecture. Measurement design is a system of dependencies. The choice of scale and the direction of causality determine which statistical tests are valid and which conclusions can be drawn. Rigorous research requires that we match our scale to the variable, verify reliability and validity, and align analysis with causal structure.